Hello, I am Zoe Paraskevopoulos and I will present the paper Compiling with Continuations Correctly. This is joint work with Anve Grover. In this paper, we present a novel technique for proving correct program transformations. Before I can dive into the details of this technique, I will talk a bit more generally about correctness of transformations. Typically, to prove that a transformation is correct, we show that it preserves the semantics of a program. In the context of this talk, this means that if a source program P computes a value, then its translation, denoted P in double brackets, computes a value with the same meaning. If the source program P diverges, then the translation of P should also diverge. Since correct compilers are also expected to asymptotically preserve the running time of source programs, we may also want to prove that our transformation preserves the running time. This means that if the source program commutes a result in m steps, then the number of steps of the translated program, m prime, should not be more than a constant factor of the number of steps of the source. Forward simulations is one of the most simple and widely used proof techniques for showing that transformations preserve semantics. This classic forward simulation diagram ascribes that whenever the source program reduces to a program P prime, then the translated program reduces with one or more steps to the translation of P prime. From this diagram, we can derive that if P computes a value V with 0, 1 or more steps, then the translation of P computes a value that is the translation of value V, which has the same meaning as V, provided that the value translation preserves the meaning of values. Furthermore, because in the simulation diagram, each source step corresponds to at least one target step, if P diverges, that is, it can take infinitely many steps, then the translation of P can also take infinitely many steps. An important aspect of forward simulations is that they facilitate compositional reasoning. Small step semantics are congruent, that is, reductions can be performed under arbitrary evaluation contexts. Furthermore, the transitive closure of the small step relation RO+, which is used to relate target programs, is of course transitive. Using these two properties, we can break a forward simulation proof into smaller pieces and reason separately about different subterms. We can then compose these proofs using congruence and transitivity. For example, say that we have to show that the translation of P steps with some number of steps to the translation of P prime. Often, the translation of P steps to some term that has a subterm that is the translation of a smaller program P1. Then, we can use the induction hypothesis to derive that if the program P1 steps to P2, then the translation of P1 steps to the translation of P2. Then, by using congruence, we show that the bigger program that has a translation of P1 as subterm steps to the same program with a subterm now substituted with a translation of P2. Now, this program can be equal or step with one or more steps to the translation of P prime, which is what we want to prove. And this is a very common proof pattern in forward simulation proofs. Unfortunately, not all transformations satisfy this simple simulation diagram. For some transformations, reductions in the source may not exactly correspond to reductions in the target language. A common reason why transformations may not satisfy the previous simulation diagram is because they introduce new binder names. In this case, the translation of P may step to a program P double prime that is not syntactically equal to the translation of P prime, but rather equal up to alpha renaming. The proof of this diagram is no longer compositional since P double prime is existentially quantified and we need to extract the existential witness from its subproof. Another reason why the symbol diagram may not hold is because some transformations introduce administrative reduction. That is, reductions that can be performed at compile time. This is the case with several continuation passing style transformations. In this scenario, the translation of P steps to a term P double prime That is not the translation of P prime, but rather the translation of P prime steps to it after performing the so-called administrative reductions. But from this diagram, we can no longer derive semantics preservation. In this paper, we make the observation that instead of relating the target programs with a small step semantics, we can use a more general relation and recover the simpler simulation diagram. In particular, we use an untyped step index logical relation. Such relations have been used before to show properties of program transformations and are well understood and reusable in many contexts. Because the logical relation assumes both alpha and beta equivalence, the simple simulation diagram holds. Furthermore, the new simulation diagram implies semantics preservation. This is because if P is logically related to a value V, then P steps to some value V prime that is equivalent to V. We are also able to recover compositionality, as the logical relation is both congruent and transitive. Therefore, the proof is compositional in the way we saw earlier. We have applied this technique to mechanically verify the continuation passing style transformation of the Certicock compiler. In particular, we saw that our CPS transformation preserves termination and divergence, and also asymptotically preserves the running time of source programs. This relation was not specifically built for the verification of the CPS transformation. It is translation independent, and it has been used in the verification of 7 other transformations of Certicock. I will now explain the application of this technique to the verification of the CPS transformation of Certicock. Because of administrative reductions, many CPS transformations, including Certicocks, do not satisfy a simple forward simulation diagram. Here, double brackets P with subscript K denotes the CPS translation of P with continuation K. In order to overcome this, Plotkin, in his seminal 1975 paper, introduces the colon translation, which is itself a CPS transformation, and reduces statically some of the administrative redexes of the CPS transformation. In order to establish a simulation for CPS, he shows that the colon translation of P steps with one or more steps to the colon translation of P prime. He then shows that the CPS translation reduces to the colon translation. From this diagram, and because the CPS translation of values coincides with the colon translation of values, one can derive semantics preservation. However, the simulation diagram is noticeably more complicated than the previous one. Even worse, in this pen and paper proof, reasoning is done implicitly up to alpha equivalence. The diagram becomes significantly more complicated when we attempt to mechanize the proof and make alpha equivalence explicit. In this diagram, the CPS translation of P steps to P1 that is alpha equivalent to the colon translation of P. The CPS translation of P prime steps to P2 that is alpha equivalent to the colon translation of P prime, and so on. So instead of proving this complicated diagram, we use our new simulation technique to establish a much simpler diagram which has a simpler and more compositional proof. From this diagram, we can derive that termination is preserved. In particular, when P reduces with some amount of steps to a value V, we have that the translation of P is related with some logical relation steps to the translation of V. By transitivity, we obtain that the translation of P is logically related to the translation of V. Then, by the definition of the logical relation, we get that the CPS translation of P reduces to a value V prime that is equivalent to V. But we still need to show divergence preservation. And for this, we need to reason about the number of steps that programs take. In particular, if the source takes m steps, it suffices to show that the target term can take m prime steps for some m prime that is larger than n. Because then, if the source program can take infinitely many steps, then so can the target. To show that running time is preserved, we should also reason about the number of steps that the source and target programs take. In particular, we want to show that if P evaluates the value V with m steps, then the translation of P evaluates the value with some number of steps m prime that is less or equal to a times m, where a is a constant. Therefore, we prove that the transformation introduces only a constant overhead and the running time of the source is asymptotically preserved. In order to show both of these properties, we need to prove that the steps of the source and target programs are related in a certain way. To do that, we parameterize the logical relation with a binary relation of program steps, which is called resource invariant. This lets us impose arbitrary relations on the number of steps of programs that are logically related. In particular, if the programs are logically related with resource invariant Q, and P1 takes C1 steps and P2 takes C2 steps, then Q of C1 and C2 is guaranteed to hold. Therefore, to show divergence and running time preservation, we need to find the right relations that we need to impose on the steps of the translation of P C1 and the steps of the translation of P prime C2. First, let's focus on divergence preservation. To show this, we need to show that the steps that the translation of P prime takes are strictly less than the steps that the translation of P takes. This way we show that for each step that happens in the source program, there is at least one step that can happen in the translated program. Therefore, when P steps with m steps to the program P prime, we have that the translation of P is related to the translation of P prime with m steps of the logical relation. Then, because of transitivity of the logical relation, we derive that the two translated programs are related with a logical relation with invariant q to the m, which denotes the composition of q with itself m times. Q to the m says that the number of steps of the translation of P, C1, is larger than the number of steps of the translation of P prime, C2, plus m. Therefore, because the translation of P prime steps to itself with 0 steps, from the definition of the logical relation, we get that the translation of P steps to a program P double prime with m prime steps. Because Q to the m holds on m prime and 0, we derive that m prime is at least as large as m. This implies divergence preservation, as the number of the target steps will be at least as many as the number of the source steps. Now, let's focus on proving that running time is preserved. To show this, we need to prove that the CPS translation can only add a constant overhead for each source step. This is captured by the resource invariant that asserts that the steps of the translation of P, C1, cannot be more than the steps of the translation of P prime, C2, plus a constant number A. Now, Q to the m also asserts that C1 is less or equal to C2 plus A times m. Therefore, because the translation of E steps to itself with 0 steps and it is a value, from the definition of the logical relation, we get that the translation of P steps with m prime steps to a value V prime that is equivalent to V. But now, we also have that m prime and 0 are related by Q to the m. From that, we obtain that m prime is less or equal to A times m, which establishes that running time is preserved. To summarize, we present a novel simulation relation which is built using a logical relation that relates the target terms. We use this proof technique to mechanically verify the CPS transformation of the certical compiler and show that termination divergence and running time are preserved. With this technique, we avoid reasoning explicitly up to alpha equivalence while using a named binary representation, which is the most common in compiler construction. In addition, we can build a simple simulation diagram that holds even if the reductions in the source language do not exactly correspond to reductions in the target language. Lastly, this technique facilitates compositional reasoning during the proof and proof reusability. Our mechanized proof is part of the Certicon compiler and is open source and available at GitHub. Thank you for watching this talk.